Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe you've been looking up at the stars, wondering what lies beyond our own galaxy. Maybe you're simply ready to drift into something vast and quiet. Either way, you're exactly where you need to be. Tonight, we're leaving the Milky Way behind and traveling to a nearby neighbor, a spiral of stars and mystery called the Triangulum Galaxy. It's smaller than our home, but no less beautiful, no less filled with wonder. We'll explore its ancient stars, its glowing nebulae, its hidden secrets. Some facts may surprise you. Others may simply wash over you like a gentle tide, easing you toward rest. If this peaceful journey helps you find calm, consider liking and subscribing. It helps others discover this quiet corner of the universe too. But for now, let yourself settle in. Take a deep breath. Let the weight of the day fall away. And let's begin our slow drift through the Triangulum Galaxy. Triangulum is the third largest galaxy in our local group. When we look out into space, we're surrounded by a collection of galaxies bound together by gravity. This neighborhood is called the local group, and it contains more than 50 galaxies. Most are small, dim dwarf galaxies, barely visible even with powerful telescopes. But 3 galaxies stand out, 3 bright spirals that dominate the group. The largest is Andromeda, a massive galaxy containing over 1 trillion stars. The second is our own Milky Way, home to several hundred billion stars. And the third is Triangulum. It's smaller than its siblings, but still vast beyond comprehension. Triangulum holds somewhere between 40 and 60 billion stars, each one a sun in its own right. Some may have planets, some may have moons, and all of them are bound together in a slow, graceful spiral, turning through the darkness like a cosmic whirlpool. Triangulum may be third in size, but is no less extraordinary. It drifts through space just 3 million light years away, close enough to study, far enough to remain mysterious. It's also known as Messier 33. In the late 1700s, a French astronomer named Charles Messier was searching the night sky for comets. But he kept finding something else, fuzzy patches of light that didn't move like comets should. To avoid confusion, he began cataloguing these objects, creating a list of things that were not comets but were still worth noting. Triangulum was the 33rd object on his list, and so it became known as Messier 33, or M33 for short. Messier didn't know what it was. He couldn't have known it was an entire galaxy, a separate island of stars far beyond our own. That understanding would come much later, but his catalogue endured, and today astronomers still use those names. When you hear someone mention M33, they're not just talking about a distant smudge of light. They're referring to an entire galaxy, a spiral of stars and gas stretching across thousands of light years. A world of worlds, catalogued centuries ago by a man looking for something else entirely. You can see it with the naked eye under perfect conditions. Most galaxies are far too faint to see without a telescope. But Triangulum is different. On a clear, moonless night, far from city lights, you can sometimes see it with just your eyes. It appears as a faint, hazy patch in the constellation Triangulum, barely visible against the background stars. It's not bright, it's not obvious, but it's there. What you're seeing is the combined light of billions of stars, so distant that their glow has been traveling through space for 3 million years. The light that reaches your eyes tonight left Triangulum long before humans walked the earth. It crossed the void while our ancestors were still learning to stand upright, still shaping their first tools. And now, in this quiet moment, that ancient light reaches you, a whisper from across the cosmos, soft enough to need darkness, patience, and a still, clear sky. Triangulum is a spiral galaxy like the Milky Way. There are many kinds of galaxies in the universe. Some are elliptical, smooth, and featureless. Others are irregular, chaotic, and unstructured. But Triangulum, like the Milky Way and Andromeda, is a spiral. When you look at it through a telescope, you can see graceful arms curving outward from a bright central core. These arms are not solid structures. They're regions where stars, gas, and dust gather, shaped by gravity and motion. The spiral pattern emerges naturally as the galaxy rotates, like water swirling down a drain. But unlike water, the stars don't fall inward. They orbit the center, held in balance by gravity and momentum. The arms glow with young, hot stars, brilliant and blue. Between them lie darker regions, still rich with gas and dust, waiting for the next generation of stars to ignite. Triangulum's spiral is open and loose, its arms spread wide, giving it a delicate, almost fragile appearance. But it's been spinning this way for billions of years, a quiet wheel turning through the dark. It contains some of the largest star-forming regions known. Scattered throughout Triangulum's spiral arms are vast clouds of gas and dust, glowing pink and red in images taken by telescopes. These are star-forming regions, places where new stars are being born. Some of these nebulae are enormous, far larger than anything found in the Milky Way. One of the most famous is called NGC 604, a massive region over 1,500 light-years across. Inside, hundreds of young, massive stars blaze with intense heat and light, ionizing the surrounding gas and making it glow. The energy from these stars carves out bubbles and cavities in the cloud, creating intricate structures that shimmer in infrared and visible light. Star formation is not a gentle process. It's violent, chaotic, and beautiful. Gravity pulls gas inward until it collapses, heats up, and ignites. The newborn stars then blast radiation and stellar winds outward, shaping their surroundings. In Triangulum, this process is happening on a grand scale, painting the galaxy with light and motion. NGC 604 is one of the brightest nebulae in the local group. Among all the glowing clouds in Triangulum, NGC 604 stands out. It's one of the brightest and largest star-forming regions in the entire local group. If it were as close to us as the Orion Nebula, it would light up our night sky, visible even in daylight. But it's not. It's 3 million light-years away, and yet we can still see it clearly through telescopes. Inside NGC 604, over 200 massive stars have formed in the last few million years. These are not ordinary stars. They're giants, tens of times more massive than our sun, burning hot and fast. Their combined light is millions of times brighter than the sun's. They won't last long, perhaps only a few million years before exploding as supernovae. But while they shine, they transform their surroundings. The nebula glows with the energy of youth, a nursery of stars carved from ancient gas. It's a reminder that even in the quiet reaches of space, creation never stops. New stars are always being born, and the universe is always beginning again. Triangulum has no central bulge like most spiral galaxies. When you look at images of spiral galaxies, you often see a bright round bulge at the center, a dense core of old stars packed tightly together. The Milky Way has one, Andromeda has one, but Triangulum does not. Its center is faint, almost flat, with no prominent bulge. This makes Triangulum unusual. Most spiral galaxies have a central concentration of stars, a remnant of their formation and evolution. But Triangulum's core is dim and spread out, suggesting a quieter history. It may never have experienced a major merger with another galaxy, the kind of violent collision that builds up a dense central bulge. Instead, it has grown slowly, peacefully, accumulating gas and forming stars at a steady pace. This gives Triangulum a delicate, ethereal quality. It's a spiral without a heavy heart, a galaxy that spins lightly through space, shaped more by time than by trauma. It's approaching the Milky Way, but very slowly. Galaxies are not stationary. They move through space, pulled by gravity, pushed by ancient momentum. Triangulum is moving too, and it's heading in our direction. Measurements show that it's approaching the Milky Way at a speed of about 24 kilometers per second. That sounds fast, but on cosmic scales, it's a leisurely drift. At this rate, it would take billions of years to close the distance between us. But the motion is there, a slow gravitational dance that connects our galaxies. Triangulum is also influenced by Andromeda, its larger neighbor. Some astronomers believe that Triangulum may be gravitationally bound to Andromeda, orbiting it like a moon orbits a planet. If that's true, then Triangulum's motion is even more complex, a three-body problem playing out over eons. For now, it remains separate, a distinct spiral spinning on its own. But in the far future, the dance may change. Collisions, mergers, and transformations may reshape the local group entirely. Triangulum may eventually merge with Andromeda. In about 4 billion years, the Milky Way and Andromeda will collide. This isn't speculation, it's prediction based on careful measurements of their motions. The two galaxies are moving toward each other, and eventually they will meet. But what about Triangulum? Some models suggest that Triangulum too may be drawn into this cosmic collision. It may merge with Andromeda before the Milky Way does, or it may join the collision later, becoming part of a larger chaotic dance. Galaxy mergers are not destructive in the way we might imagine. Stars are so far apart that they rarely collide. Instead, the galaxies pass through each other, their shapes distorting, their spiral arms stretched and torn. Over time, they blend together, forming a new, larger galaxy. Triangulum's fate is uncertain. It may survive as a separate entity, or it may become part of something new. Either way, the slow ballet of the local group continues, guided by gravity and time. The galaxy is about 60,000 light-years across. Triangulum is vast, but not as vast as its neighbors. It stretches about 60,000 light-years from edge to edge, making it roughly half the size of the Milky Way. That's still an almost incomprehensible distance. Light, traveling at 300,000 kilometers per second, takes 60,000 years to cross from one side of Triangulum to the other. If you could somehow travel at the speed of light, you would still spend tens of thousands of years journeying through this single galaxy. And within that space, billions of stars orbit, each one separated from its neighbors by vast stretches of emptiness. Triangulum is not crowded. It's spacious, elegant, and quiet. A spiral of light turning slowly through the void, held together by gravity, shaped by motion, and filled with the faint glow of distant suns. It contains hundreds of globular clusters scattered around Triangulum. Both in its spiral arms and in the space beyond are hundreds of globular clusters. These are dense, spherical collections of stars, each containing thousands to millions of stars packed tightly together. Globular clusters are ancient, some of the oldest structures in the galaxy. They formed early in Triangulum's history, long before most of its stars were born. Inside a globular cluster, stars are so close together that the night sky would be ablaze with light. If you stood on a planet inside such a cluster, you might see hundreds or even thousands of stars brighter than Venus, casting multiple shadows on the ground. But these clusters are also quiet. The stars inside are old, cool, and red, long past their youth. They drift through space in a slow gravitational ballet, orbiting the center of Triangulum in long elliptical paths. Some may eventually be stripped away, torn apart by tidal forces, but for now, they remain ancient relics of a galaxy's early days. Triangulum rotates, but not like a solid disk. Galaxies are not rigid objects. They don't spin like wheels. Instead, they rotate differentially, meaning different parts move at different speeds. In Triangulum, stars closer to the center orbit faster than those farther out, though the relationship is more complex than simple physics would predict. This is partly due to dark matter, an invisible substance that makes up most of the galaxy's mass. Dark matter doesn't emit light, so we can't see it directly, but we can see its effects on the motion of stars and gas. Without dark matter, the outer regions of Triangulum would spin so slowly they'd drift apart. But they don't. They hold together, moving faster than expected, held in place by gravity from something unseen. This mystery is one of the deepest in astronomy. We know dark matter is there. We can measure its influence, but we don't yet know what it's made of. In Triangulum, as in every galaxy, the invisible holds the visible together. Its stars span a wide range of ages. Look closely at Triangulum, and you'll find stars of all ages. Some are ancient, born billions of years ago when the galaxy was young. These old stars are red and cool, clustered in the halo and in globular clusters. Others are newborns, blue and blazing hot, found in the spiral arms where star formation is still happening. This mix of ages tells a story. Triangulum hasn't formed all its stars at once. It's been building itself slowly over time, converting gas into stars in waves and bursts. Each generation of stars lives, dies, and enriches the galaxy with heavier elements. Those elements are then incorporated into the next generation. The oldest stars contain almost nothing but hydrogen and helium, the raw materials left over from the Big Bang. The youngest stars contain carbon, oxygen, iron, all the elements needed to build planets and, eventually, life. Triangulum is a living archive, a record of cosmic evolution written in starlight. Some of its stars are more massive than the Sun. Not all stars are created equal. In Triangulum, as in every galaxy, stars come in a wide range of sizes and masses. Some are small, cool red dwarfs, barely massive enough to sustain fusion. Others are giants, tens or even hundreds of times more massive than the Sun. These massive stars are rare, but they dominate the light and energy output of the galaxy. They burn hot and blue, consuming their fuel at a furious rate. A star 50 times the mass of the Sun might only live for a few million years before exploding as a supernova. But during that brief life, it shines with the light of 1,000,000 suns. These massive stars shape their surroundings. They ionize gas, trigger new star formation, and eventually scatter heavy elements across the galaxy when they die. They're the engines of galactic evolution, short-lived, but transformative. In Triangulum's star-forming regions, these giants are being born even now, adding their light to the spiral's glow. The galaxy is rich in neutral hydrogen gas. Spread throughout Triangulum is a vast reservoir of neutral hydrogen, the simplest and most abundant element in the universe. This gas doesn't glow on its own. It's cold and dark, invisible to optical telescopes. But radio telescopes can detect it, tuned to the specific wavelength of light that hydrogen emits. Maps of Triangulum in radiolight reveal enormous clouds of hydrogen filling the spaces between stars, especially in the spiral arms. This gas is the raw material for future stars. Given enough time, gravity will pull it together, compress it, and ignite it. The hydrogen will become helium, and light will shine where there was only darkness. Triangulum is still actively forming stars, and its hydrogen reserves are the reason why. As long as the gas remains, the galaxy can continue to grow, to shine, to create. It's a slow process, measured in millions of years, but it's happening now, quietly, invisibly, in the cold depths of space. Dust lanes trace the spiral arms between the stars. Triangulum is filled with dust, tiny grains of carbon, silicates, and ice, each smaller than a speck of pollen. These grains gather in the spiral arms, forming dark lanes that block the light of stars behind them. In images of Triangulum, you can see these dust lanes clearly, winding through the galaxy like rivers of shadow. Dust may seem insignificant, but it plays a vital role in the life of a galaxy. It absorbs starlight and re-emits it as infrared radiation, cooling the gas and allowing it to collapse more easily. It also provides surfaces where molecules can form, building the complex chemistry needed for planets and, eventually, life. When you look at Triangulum, the dark lanes aren't empty. They're full of potential regions where the next generation of stars is waiting to be born. Dust is not the absence of light. It's the promise of what comes next. Triangulum has been studied for over a century. Astronomers have been observing Triangulum for more than 100 years, long before they understood what it truly was. In the early 1900s, many believed that spiral nebulae like Triangulum were clouds of gas within the Milky Way, not separate galaxies. It wasn't until the 1920s, when Edwin Hubble measured the distance to Andromeda, that the true scale of these objects became clear. Triangulum was not a cloud. It was a galaxy, an entire system of stars far beyond our own. Since then, astronomers have studied it in every wavelength of light, from radio waves to X-rays. They've mapped its stars, its gas, its dust. They've tracked its motion, measured its mass, and modeled its history. Each new observation adds another piece to the puzzle. Triangulum is no longer a mystery, but a subject of ongoing investigation. And with each discovery, it becomes more familiar, more understood, and somehow more beautiful. The galaxy is moving through space at over 100 kilometers per second. Everything in the universe is in motion. The Earth orbits the Sun orbits the center of the Milky Way, and the Milky Way itself is moving through space. So is Triangulum. Relative to the cosmic microwave background, the faint glow left over from the Big Bang, Triangulum is moving at a speed of over 100 kilometers per second. That's not motion through some fixed grid of space. It's motion relative to the universe itself, to the framework of expansion and gravity that holds everything together. This motion is the result of countless gravitational pulls ancient momentum from the galaxy's formation, the influence of nearby galaxies, and the large-scale structure of the cosmos. Triangulum doesn't move in a straight line. It dances, pulled and pushed by invisible forces, drifting through the void, on a path shaped by billions of years of history. It has a low surface brightness compared to other galaxies when you look at Triangulum through a telescope. It's surprisingly faint. Even though it contains tens of billions of stars, those stars are spread out over a large area, giving the galaxy a low surface brightness. This makes it harder to see than you might expect. You need dark skies, clear air, and patience. The faintness isn't because the stars are dim, it's because they're distributed diffusely. Triangulum doesn't have a bright central bulge to concentrate light. Its spiral arms are open and loose. The result is a galaxy that glows softly, almost gently, like a ghost against the darkness. This low surface brightness also makes Triangulum an excellent target for studying galactic structure. There's less light pollution from the core, so astronomers can see the spiral arms, the star-forming regions, and the distribution of gas more clearly. It's a galaxy that reveals its secrets slowly, quietly, to those willing to look closely. Some of its stars will explode as supernovae in Triangulum, as in every galaxy. Some stars are destined for a violent end. Massive stars, those more than 8 times the mass of the Sun, don't fade gently, they explode. When these stars exhaust their nuclear fuel, their cores collapse in a fraction of a second, triggering a supernova, one of the most energetic events in the universe. For a few weeks, a single exploding star can shine as brightly as the entire galaxy. The explosion scatters heavy elements into space: carbon, oxygen, iron, gold, enriching the surrounding gas and seeding future generations of stars and planets. In Triangulum, supernovae have been erupting for billions of years, shaping the galaxy's chemistry and structure. Some of those explosions may have triggered new waves of star formation. Others may have blown gas out of the galaxy entirely. And more are coming. Right now, in some distant corner of Triangulum, a massive star may be nearing the end of its life, preparing to light up the spiral with one final brilliant flash. Triangulum has been imaged by the Hubble Space Telescope. In 2019, the Hubble Space Telescope released one of the most detailed images of Triangulum ever taken. The image combined 54 separate observations, creating a mosaic that revealed over 25 million individual stars. It's a breathtaking view, a portrait of an entire galaxy in stunning clarity. You can see the spiral arms winding through the frame, dotted with bright blue star clusters and glowing pink nebulae. You can trace the dark dust lanes, the yellow glow of older stars, and the faint halo surrounding the galaxy. Each point of light is a sun, perhaps with its own family of planets, its own moons, its own quiet corner of the universe. This image is more than a photograph. It's a window into another world, a reminder that beyond our sky, beyond our galaxy, there are others equally vast, equally full of stories. And Triangulum, captured in exquisite detail, becomes not just a distant object, but something real, tangible, and beautiful. The galaxy has a relatively low metallicity. In astronomy, metals refers to any element heavier than hydrogen and helium. These elements, carbon, oxygen, iron, and so on, are created inside stars and scattered into space when stars die. The amount of these metals in a galaxy is called its metallicity. Triangulum has a lower metallicity than the Milky Way, meaning it contains fewer heavy elements relative to its hydrogen and helium. This suggests that Triangulum has formed stars more slowly than the Milky Way, giving it less time to enrich its gas with heavy elements, or perhaps it has lost some of its metal-rich gas through galactic winds, blown away by supernova explosions and stellar radiation. Lower metallicity also affects the kinds of stars that form. With fewer heavy elements, the gas cools less efficiently, and stars tend to be more massive on average. This can lead to more intense star formation events, brighter nebulae, and more frequent supernovae. Triangulum's chemistry is a clue to its history, a record written in the faint traces of elements scattered through its spiral arms. It contains both open and globular star clusters. Star clusters come in two main types, and Triangulum has both. Open clusters are loose groupings of young stars found in the spiral arms where star formation is happening. They contain dozens to hundreds of stars, all born from the same cloud of gas, all roughly the same age. These clusters are not tightly bound by gravity, and over time, they drift apart as their stars wander off into the galaxy. Globular clusters, on the other hand, are ancient and dense. They contain thousands to millions of old stars, packed into a sphere just tens of light years across. These clusters orbit in the halo of the galaxy, far from the spiral arms. They're survivors from the galaxy's early days, relics of a time when Triangulum was just beginning to form. In Triangulum, both types of clusters coexist, young and old, loose and tight. Each tells a different part of the galaxy's story, from its birth to the present day. The spiral arms are not permanent structures. When you look at Triangulum's spiral arms, it's easy to imagine them as solid, unchanging features. But they're not. The arms are density waves, regions where stars, gas, and dust pile up temporarily as they orbit the galaxy. Think of it like a traffic jam on a highway. The cars move through the jam, but the jam itself stays in place. In the same way, stars and gas move through the spiral arms, but the arms themselves persist. As material enters an arm, it slows down slightly, compressed by gravity. This compression triggers star formation, creating the bright blue stars and glowing nebulae that make the arms visible. Then the material moves on, leaving the arm behind. The arms don't rotate as solid structures. They're waves of density, patterns in the flow of matter shaped by gravity and motion. In this sense, Triangulum's spiral is not a thing, but a process, a rhythm playing out over millions of years. Triangulum is one of the most studied nearby galaxies. Because it's so close, Triangulum has become a laboratory for understanding how galaxies work. Astronomers study its star-forming regions to learn how stars are born. They map its gas to understand how galaxies accumulate fuel. They track its motion to probe the distribution of dark matter. Every observation of Triangulum adds to our knowledge, not just of this one galaxy, but of galaxies in general. It's close enough to study in detail, but far enough to show us what a galaxy looks like from the outside. We can't step back and see the Milky Way the way we see Triangulum. We're inside it, surrounded by its stars. But Triangulum gives us perspective. It shows us what a spiral galaxy looks like, how it behaves, and how it evolves. It's a mirror, reflecting truths that we can then apply to our own cosmic home. Some regions of Triangulum are forming stars rapidly, star formation is not evenly distributed across Triangulum. Some regions are quiet, filled with old stars and little gas. Others are ablaze with activity, forming new stars at a rapid pace. These star-forming regions, called H2 regions, are clouds of ionized hydrogen glowing with the energy of young, massive stars. In some parts of Triangulum, dozens of these regions cluster together, creating bright knots of light that stand out even in images taken from millions of light years away. The rate of star formation in Triangulum is modest compared to some galaxies, but it's still significant. Every year, the galaxy converts thousands of solar masses of gas into new stars. This process will continue for billions of years, as long as the gas supply holds out. And when the gas is finally exhausted, Triangulum will grow quiet, its spiral arms fading, its glow dimming into the deep red of aging stars. The galaxy's rotation curve reveals the presence of dark matter. One of the most important discoveries about Triangulum came from measuring how fast its stars and gas are moving. By studying the rotation curve, the graph of orbital speed versus distance from the center, astronomers found something unexpected. The outer regions of the galaxy are moving faster than they should. According to the visible mass of stars and gas, the outer parts should be moving slowly, barely held by gravity. But they're not. They're moving fast, as if there's more mass than we can see. This discrepancy is evidence for dark matter, an invisible substance that surrounds and permeates the galaxy. Dark matter doesn't emit, absorb, or reflect light, so we can't see it. But its gravity affects the motion of everything around it. In Triangulum, dark matter outweighs visible matter by a factor of at least 5-1. It's the unseen scaffold that holds the galaxy together, the hidden hand that shapes its motion and its form. Triangulum's light has been traveling for 3 million years. When you look at an image of Triangulum, you're not seeing it as it is now. You're seeing it as it was. The light captured by telescopes left the galaxy 3 million years ago, when Earth was a very different place. Our ancestors were just beginning to walk upright. The climate was shifting. Ice ages were coming and going, and all the while, light from Triangulum was traveling through space, crossing the void at 300,000 kilometers per second. During those 3 million years, stars were born in Triangulum. Others died. Gas clouds collapsed. Supernovae exploded. The galaxy continued its slow rotation, oblivious to the fact that one day its light would reach a small blue planet where curious beings would point telescopes skyward and wonder. What we see is not the present, but the past. And by the time our observations reach Triangulum, if light could carry them back, another 3 million years will have passed. We are observers across time studying ancient light, forever separated from the moment we're trying to see. The galaxy has no known supermassive black hole at its center. Most large galaxies have a supermassive black hole lurking at their core, a gravitational monster millions or billions of times the mass of the Sun. The Milky Way has one, Andromeda has one, but Triangulum might not. Observations of the galaxy's center show no clear evidence of a supermassive black hole. The stars there move too slowly, their orbits too gentle to suggest the presence of a massive dark object. This makes Triangulum unusual. It's one of the largest galaxies we know of that might lack a central black hole. Or perhaps the black hole is there, just smaller than expected, hidden in the faint glow of the core. Either way, Triangulum's quiet heart sets it apart. It's a galaxy without a monster, a spiral that turns peacefully, untroubled by the gravitational chaos that dominates so many other galactic centers. And in that quietness, there's a kind of grace. Some of its stars may have planets. We haven't detected any planets in Triangulum, not yet. The galaxy is too far away for current technology to see individual planets orbiting its stars. But that doesn't mean they're not there. Planets are common in the universe. Nearly every star in the Milky Way has at least one planet, and there's no reason to think Triangulum would be any different. Somewhere in that spiral, orbiting one of those 40 or 60 billion suns, there may be worlds, rocky planets, gas giants, moons with hidden oceans. Some may be scorched and lifeless. Others may be frozen and dark. But a few, just a few, might be in the right place, at the right distance, with the right conditions for liquid water, for chemistry, for life. We can't see them. We can't visit them. But in the quiet glow of Triangulum, they may exist. Worlds we'll never know, spinning silently through the dark, lit by distant stars. Triangulum's spiral pattern is relatively open and loose. Not all spiral galaxies look the same. Some have tight, well-defined arms wrapped closely around a bright core. Others, like Triangulum, have open, loose spirals that spread out gracefully. Triangulum's arms are not sharp or tightly wound. They're soft and diffuse, giving the galaxy a delicate, almost ethereal appearance. This open structure may be the result of Triangulum's history. Without a major merger to compress and reshape it, the galaxy has evolved gently. Its arms drift outward, traced by young stars and glowing gas, but never gripping tightly to the center. Some astronomers classify Triangulum as an SASCD galaxy in the Hubble sequence, meaning it's a spiral with no bar, loosely wound arms, and a faint core. It's a classification, a label, but it also tells a story. A story of a galaxy that has grown slowly, peacefully, without the violent disruptions that mark so many others. The galaxy is tilted at an angle from our perspective. When we look at Triangulum, we're not seeing it edge-on or face-on, but somewhere in between. The galaxy is tilted at an angle of about 54 degrees relative to our line of sight. This gives us a beautiful, three-dimensional view of its structure. We can see the spiral arms winding through space, the dust lanes cutting across them, and the way the galaxy stretches out in depth, not just width. This angle is fortunate. If Triangulum were edge-on, we'd see only a thin line, its structure flattened and obscured by dust. If it were face-on, we'd lose the sense of depth, seeing only a flat spiral. But at this intermediate angle, Triangulum reveals itself fully, showing us both its shape and its substance. It's a galaxy posed perfectly for study, for photography, for quiet contemplation on a dark night. Astronomers have used Triangulum to study stellar populations. Because Triangulum is close enough to resolve individual stars, astronomers use it as a testing ground for understanding stellar populations. They can separate young, hot blue stars from old, cool red ones. They can identify supergiant stars, measure their brightness, and use them as distance indicators. They can study how stars of different masses and ages are distributed throughout the galaxy. This work helps refine our understanding of stellar evolution, the life cycles of stars from birth to death. By studying Triangulum, astronomers learn not just about this one galaxy, but about how stars behave everywhere, in all galaxies, throughout the universe. Triangulum becomes a classroom, a place where the principles of astrophysics can be tested and refined. And every observation, every measurement, adds another piece to the larger picture of how galaxies and stars evolve together over cosmic time. The galaxy's outer regions are rich in young stars, while many galaxies concentrate their star formation in the center or spiral arms. Triangulum shows active star formation even in its outer regions. Young, bright stars can be found far from the galactic core, scattered through the outskirts where the gas is thinner and the gravity weaker. This extended star formation is unusual and not fully understood. It may be the result of gas falling into the galaxy from outside, or interactions with nearby galaxies that stir up the outer regions. Either way, it shows that Triangulum is still actively growing, still building new stars even at its edges. The galaxy is not winding down. It's still alive, still vibrant, still turning gas into light across its entire span. And in those distant corners, far from the bright core, new stars are blinking into existence, adding their glow to the spiral's ancient light. Triangulum may have been disturbed by past interactions. Though Triangulum appears peaceful now, it may not always have been so. Some astronomers believe that the galaxy's structure shows subtle signs of past disturbances, perhaps from a close encounter with another galaxy. There are faint asymmetries in its spiral arms, slight warps in its outer regions, and irregular distributions of gas. These features could be the result of a gravitational interaction, a close pass by another galaxy that pulled on Triangulum's stars and gas, stirring them up and leaving behind subtle scars. The most likely culprit is Andromeda, Triangulum's larger neighbor. The two galaxies may have passed close to each other in the distant past, close enough to disturb each other's structure without fully merging. If so, Triangulum carries the memory of that encounter, a faint echo written in the motion of its stars, and in the future, the two may interact again, shaping each other once more. The galaxy's mass is dominated by dark matter. When you add up all the stars, gas, and dust in Triangulum, you get a total mass of about 50 billion times the mass of the Sun. That's enormous, but it's not the whole story. When astronomers measure the galaxy's total mass by studying how fast things are moving, they find something much larger, closer to 200 or 300 billion solar masses. Where is the missing mass? It's dark matter. This invisible substance makes up the majority of Triangulum's mass, surrounding the visible galaxy in a vast, spherical halo. We can't see it, touch it, or detect it directly, but its gravity shapes everything we observe. Without dark matter, Triangulum would fly apart. Its stars would drift away. Its gas would disperse. The galaxy exists only because dark matter holds it together. It's the invisible foundation, the unseen scaffold, the hidden majority that makes the visible minority possible. Triangulum's stars formed over billions of years. The stars in Triangulum didn't all form at once. They've been born in waves and bursts over the galaxy's entire history, spanning billions of years. The oldest stars, found in the halo and globular clusters, formed when the galaxy was young, perhaps 10 or 12 billion years ago. The youngest stars, blazing in the spiral arms, were born just a few million years ago. In between, countless generations have come and gone. Each wave of star formation used up some of the galaxy's gas, enriched it with heavy elements, and set the stage for the next generation. This layered history is visible in the colors of Triangulum's light. Old stars glow red and yellow. Young stars burn blue and white. Together, they create a spectrum that tells the story of the galaxy's life, a story still being written, still unfolding, one star at a time. Some nebulae in Triangulum glow in multiple wavelengths. When astronomers observe Triangulum star-forming regions, they don't just use visible light. They also look in ultraviolet, infrared, radio, and X-ray wavelengths. Each wavelength reveals something different. In visible light, we see the glow of ionized gas, pink and red from hydrogen, blue and green from oxygen. In ultraviolet, we see the hottest, youngest stars blazing with energy. In infrared, we see the warm dust that surrounds newborn stars, glowing like embers. And in radio wavelengths, we see the cold molecular clouds where stars are just beginning to form. By combining these views, astronomers build a complete picture of what's happening in these regions. They can see the entire life cycle of star formation, from cold gas collapsing to hot stars igniting, to the eventual dispersal of the gas by stellar winds and supernovae. Triangulum becomes a laboratory, each nebula a window into the processes that shape galaxies everywhere. The galaxy has been photographed by amateur astronomers. You don't need $1 billion space telescope to see Triangulum. Amateur astronomers with backyard telescopes have been photographing it for decades. With a good telescope, a camera, and a dark sky, you can capture the galaxy's spiral structure, its star-forming regions, even some of its brighter star clusters. These images may not have the resolution of Hubble, but they carry something else, a personal connection. When you photograph Triangulum yourself, it's no longer just a distant object in a textbook. It becomes something you've seen, something you've captured, something real. Amateur astronomers have contributed to science by monitoring Triangulum, tracking supernovae, and documenting changes over time. Their observations complement professional work, filling in gaps and providing long-term records. In this way, Triangulum belongs not just to scientists, but to anyone with a telescope and a sense of wonder. Triangulum's gas extends beyond its visible edge. The visible part of Triangulum, the glowing spiral we see in images, is not the whole galaxy. Beyond the stars, beyond the bright nebulae, there are vast clouds of neutral hydrogen gas stretching far into space. These clouds don't emit visible light, but radio telescopes can detect them, revealing a galaxy much larger than it appears. This extended gas halo may be the remnant of Triangulum's formation, primordial gas that was never incorporated into stars. Or it may be gas that was expelled by supernova explosions and stellar winds, then fell back under gravity. Either way, it surrounds the galaxy like a faint, invisible envelope. In the far future, some of this gas may fall inward, fueling new waves of star formation. Or it may be stripped away by interactions with other galaxies, lost to the void. For now, it drifts quietly, a reservoir of potential waiting. The galaxy's rotation period varies with distance. In Triangulum, stars closer to the center complete an orbit in just tens of millions of years. Stars farther out take hundreds of millions of years to circle once around the core. This differential rotation is what creates and maintains the spiral arms, stretching and shearing the gas and dust into graceful curves. But it also means that Triangulum doesn't rotate as a single, solid object. Different parts move at different speeds, like gears turning at different rates. The galaxy is fluid, dynamic, constantly reshaping itself, and yet, somehow, the overall pattern persists. The spiral arms remain, the structure endures, even as individual stars and gas clouds orbit at their own pace. It's a delicate balance between motion and form, between chaos and order, a dance choreographed by gravity and time. Astronomers have studied Triangulum's chemical composition. By analyzing the light from Triangulum's stars and gas, astronomers can determine what elements are present and in what quantities. They look for spectral lines, specific wavelengths of light that correspond to particular elements. Hydrogen, helium, carbon, oxygen, nitrogen, iron, each has its own signature. What they found is that Triangulum is less chemically enriched than the Milky Way. It has fewer heavy elements, suggesting a slower, steadier history of star formation. This lower metallicity affects everything: the kinds of stars that form, the chemistry of the gas, the properties of planets that might exist there. It's a reminder that not all galaxies are the same. Each has its own history, its own chemistry, its own story. And Triangulum's story is one of patience, of gradual growth, of a galaxy that has taken its time. Some stars in Triangulum are variable. Not all of Triangulum's stars shine with a steady light. Some are variable stars, changing in brightness over time. These changes can be regular or irregular, rapid or slow, depending on the type of star. Cepheid variables, for example, pulse in and out, brightening and dimming in a rhythm that depends on their intrinsic luminosity. These stars are incredibly useful for measuring distances, since their period tells us how bright they truly are. By comparing that to how bright they appear, we can calculate how far away they are. Astronomers have used Cepheid variables in Triangulum to refine its distance, confirming that it lies about 3 million light-years away. Other variable stars in Triangulum include eclipsing binaries, stars that dim when one passes in front of the other, and eruptive variables, stars that flare or fade unpredictably. Each one adds to the symphony of light coming from the galaxy, a chorus of stars singing in different keys. Triangulum has inspired art and imagination for centuries, long before we knew what Triangulum was. It inspired wonder. Ancient astronomers saw it as a faint smudge in the sky, mysterious and distant. Artists imagined what it might be: a cloud, a portal, a gathering of souls. In modern times, Triangulum has appeared in science fiction, in paintings, in poems. It represents the unknown, the distant, the unreachable. It's a symbol of the vastness of space and the limits of human knowledge. But it's also a symbol of curiosity. We may never visit Triangulum, never walk on its worlds, never see its stars up close. But we can study it, understand it, and appreciate it. And in that appreciation, we find something deeply human, a desire to connect with the cosmos, to understand our place in it, and to reach beyond ourselves toward the distant light. The galaxy's structure has been modeled in simulations. To understand how Triangulum formed and evolved, astronomers don't just observe it, they also simulate it. Using powerful computers, they model the galaxy's history, starting with a cloud of gas billions of years ago and letting gravity, gas dynamics, and star formation play out over time. These simulations help answer questions that observations alone cannot. How did Triangulum's spiral arms form? Why does it lack a central bulge? What role did dark matter play in its evolution? By comparing simulations to real observations, astronomers refine their models and improve their understanding. Triangulum becomes a test case, a way to check whether our theories of galaxy formation match reality. And when the simulations succeed, When they produce a galaxy that looks like Triangulum, it's a quiet triumph, a sign that we're getting closer to understanding how the universe works. Some of Triangulum's stars will become white dwarfs. Not all stars end their lives in spectacular explosions. Most, including stars like our Sun, die more gently. After exhausting their nuclear fuel, they shed their outer layers into space, forming a planetary nebula. What remains is the core, a dense, hot object called a white dwarf. White dwarfs are incredibly dense, packing a mass similar to the Sun's into a sphere the size of Earth. They no longer produce energy through fusion. They simply radiate away their leftover heat, slowly cooling over billions of years. In Triangulum, countless stars have already become white dwarfs, scattered throughout the galaxy. They're faint and difficult to detect, but they're there, quiet remnants of stars that once shone brightly. And in the far future, when Triangulum's last stars have burned out, white dwarfs will be all that remain, cooling embers in an aging galaxy. Triangulum's disk is relatively thin. Galaxies have structure not just in width, but in depth. Triangulum's stellar disk, the flattened region where most of its stars reside, is relatively thin, just a few hundred light years from top to bottom. This thinness is the result of rotation and gravity. As the galaxy formed, gas settled into a spinning disk, flattened by angular momentum. Stars born from that gas inherited the disk's shape, but not all stars stay in the disk. Some are kicked out by gravitational interactions or supernova explosions, ending up in the halo above and below. These halo stars are older, redder, and more scattered. They orbit in random directions, not confined to the disk's orderly rotation. The result is a layered structure, a thin disk surrounded by a diffuse halo. And in that layering, we see the galaxy's history, its youth in the disk, its age in the halo, its life written in 3 dimensions. The galaxy is a benchmark for distance measurements. Triangulum plays an important role in the cosmic distance ladder, the series of methods astronomers use to measure distances across the universe. Because it's close enough to resolve individual stars, astronomers can identify Cepheid variables and other distance indicators within it. By measuring how bright these stars appear and comparing that to their known intrinsic brightness, they can calculate Triangulum's distance with high precision. This distance then serves as a calibration point for other methods. If we know how far Triangulum is, and we can see similar objects in more distant galaxies, we can extend our measurements outward. Step by step, rung by rung, we climb the distance ladder, reaching farther into space. Triangulum is one of the early rungs, a foundation that helps us map the universe. Some of its stars are surrounded by dust shells. In the later stages of their lives, some stars in Triangulum begin to shed their outer layers, losing mass through strong stellar winds. This material, rich in heavy elements, forms a shell of dust and gas around the star. These dust shells glow in infrared light, warmed by the dying star at their center. They're not bright, invisible light, but infrared telescopes like Spitzer and James Webb can detect them, revealing dozens or even hundreds of these evolved stars scattered throughout Triangulum. These stars are contributing to the galaxy's chemical enrichment, returning carbon, oxygen, and other elements to the interstellar medium. When they finally die, their dust will mix with the surrounding gas, becoming part of the next generation of stars. In this way, Triangulum recycles itself, each generation of stars feeding the next, a cosmic cycle of death and rebirth. Triangulum's halo contains ancient stellar streams. Surrounding Triangulum, far from the bright spiral arms, is a faint halo of old stars. This halo is not smooth. It contains subtle structures, streams and clumps of stars that trace the remains of smaller galaxies that merged with Triangulum long ago. These stellar streams are the ghosts of past interactions, evidence that Triangulum, like most galaxies, grew by consuming its smaller neighbors. When a dwarf galaxy falls into a larger one, it's torn apart by tidal forces. Its stars are scattered along its orbit, forming a stream that eventually spreads out and blends into the halo. By studying these streams, astronomers can reconstruct Triangulum's history, identifying the galaxies it absorbed and learning about its growth over time. The halo is a memory, a record written in starlight, of all the smaller worlds that became part of something larger. The galaxy's magnetic field is weak but present. Like many spiral galaxies, Triangulum has a magnetic field threading through its disk. This field is incredibly weak, millions of times weaker than a refrigerator magnet. But on galactic scales, it matters. The magnetic field helps shape the motion of charged particles, influences star formation, and plays a role in how gas moves through the galaxy. Astronomers detect this field by observing the polarization of light from Triangulum and by studying radio emission from charged particles spiraling along magnetic field lines. The field isn't uniform. It's tangled and twisted, shaped by the rotation of the galaxy and by turbulence in the gas. In some regions, it follows the spiral arms. In others, it loops and knots in complex patterns. This magnetic field is one more layer of structure in Triangulum, invisible but present, threading through the galaxy like a quiet current. Triangulum has no known active galactic nucleus. Many galaxies have active nuclei. Regions where a supermassive black hole is actively feeding on gas and shining brightly across the electromagnetic spectrum. But Triangulum is quiet. Its core shows no signs of intense activity, no jets, no bright emission, no rapidly moving gas. If there is a black hole at the center, it's either very small or not actively consuming material. This quietness makes Triangulum different from many other galaxies. It's not powered by a central engine. Its light comes entirely from stars, from the combined glow of billions of suns burning through their fuel. There's something peaceful about that, a galaxy that shines not from a violent core, but from the steady, patient work of countless stars. A light born from fusion, not from the chaos of a black hole's appetite. The galaxy's future is tied to the local group Triangulum doesn't exist in isolation. Its motion, its structure, and its fate are all tied to the other galaxies in the local group. Over the next few billion years, gravity will continue to pull the group together. Andromeda and the Milky Way will collide. Smaller galaxies will be absorbed or disrupted, and Triangulum will be part of that drama. Whether it merges with Andromeda first, or remains separate until the Milky Way collision, or somehow survives as an independent galaxy, we don't yet know. The dynamics are complex, shaped by gravity, dark matter, and the initial conditions of the local group. But one thing is certain, Triangulum's future will be different from its past. The peaceful spiral we see today may one day be transformed, reshaped, or absorbed. The galaxy story is not finished. It's still being written, one gravitational pull at a time. Astronomers continue to discover new details about Triangulum every few years. New telescopes, new techniques, and new observations reveal something unexpected about Triangulum. A previously unknown star cluster, a faint stellar stream, a peculiar motion in the gas. Each discovery adds to our understanding, but also raises new questions. Science is not about finding final answers. It's about asking better questions. And Triangulum, despite being studied for over a century, still has secrets, still has mysteries, still has details waiting to be uncovered by the next generation of astronomers, the next telescope, the next careful observer looking closely at the light from 3 million years ago. The galaxy is familiar but not fully known, and that gap between knowledge and mystery is where wonder lives. The spiral arms contain young, bright star clusters scattered through Triangulum's spiral arms are dozens of open star clusters, groups of young stars born from the same cloud of gas. These clusters are bright and blue, dominated by massive stars that shine intensely but briefly. Some clusters contain just a few dozen stars, others hold hundreds. They're not gravitationally bound as tightly as globular clusters, so over time, they drift apart. But while they last, they're stunning. In images of Triangulum, they appear as bright knots of light, like jewels strung along the spiral arms. These clusters are laboratories for studying star formation. All the stars in a cluster are the same age and started with the same composition. So any differences between them must be due to their masses. By studying these clusters, astronomers learn how stars of different sizes evolve, how long they live, and how they die. Triangulum's light contributes to the cosmic background. Even though Triangulum is just one galaxy among billions, its light contributes to the overall glow of the universe. When astronomers measure the cosmic optical background, the faint light that fills space, they're detecting the combined emission from all the galaxies, stars, and glowing gas in the universe. Triangulum is part of that glow. Its photons travel outward in all directions, some reaching us, others heading into the depths of intergalactic space where they may never encounter another galaxy, another observer, or anything at all. They'll just keep traveling, redshifted by the expansion of space, growing fainter and fainter until they're lost in the darkness. But for now, Triangulum shines, adding its voice to the cosmic chorus, a small contribution to the light of the universe. Some of its gas may have been stripped by interactions when galaxies pass close to each other. Their gravity can pull at each other's gas, stripping it away and leaving it drifting in the space between them. Some astronomers believe that Triangulum may have lost gas in this way, perhaps during a past interaction with Andromeda. This lost gas would have been pulled out of the galaxy, too far to fall back, and left to float in the intergalactic medium. Losing gas affects a galaxy's future. Without gas, new stars can't form. The galaxy slowly fades as its existing stars age and die. Triangulum is still forming stars, so it hasn't lost all its gas. But it may have lost some, and that loss may shape its long-term evolution. In the quiet spaces between galaxies, that stolen gas drifts, a reminder that even in the vastness of space, galaxies touch, influence, and change each other. The galaxy is visible from both hemispheres. Unlike some deep sky objects that can only be seen from one part of the Earth, Triangulum is visible from both the northern and southern hemispheres. though it's easier to see from the north. In the northern hemisphere, it's a late summer and autumn object, rising high in the sky during the evenings. In the southern hemisphere, it stays lower on the horizon, harder to see but still accessible with a good telescope and a clear view to the north. This accessibility has made Triangulum a favorite target for amateur astronomers around the world. Whether you're in North America, Europe, Australia, or anywhere in between, you can point your telescope toward the constellation Triangulum and see the faint glow of this distant spiral. It's a shared sky, a common wonder, a galaxy that belongs to everyone willing to look up. Triangulum reminds us of our place in the universe. When you look at Triangulum, you're looking at an entire galaxy, billions of stars, trillions of planets possibly, all spinning through space 3 million light years away. And yet, the light from that galaxy reaches us, crosses the void, and lands on a telescope mirror or in your eye. In that moment, a connection is made. Not physical, but real. We are part of the same universe. We're made of the same atoms. We're governed by the same laws. And we share the same darkness, the same light, the same quiet mystery. Triangulum doesn't know we exist. It doesn't care. But we know it exists. We study it, photograph it, wonder about it. And in doing so, we connect ourselves to something larger, something older, something that was shining long before we were here and will continue long after we're gone. The galaxy will continue to change over billions of years. Triangulum is not frozen in time. It's evolving, changing, growing. Every year, it forms new stars. Every few decades, a star explodes. Every million years, its structure shifts slightly, shaped by gravity and motion. Over the next billion years, Triangulum will continue to spin, to shine, to transform. Some of its gas will be converted into stars. Some will be lost. Its spiral arms may tighten or loosen. Its interactions with Andromeda and the Milky Way may reshape it entirely. But for now, in this moment, Triangulum is what it is, a beautiful spiral galaxy, close enough to see, far enough to inspire, old enough to carry history, and young enough to still be alive with light. And in the quiet of this moment, it turns, glowing softly, a wheel of stars spinning through the dark. And now, as we reach the end of our journey through the Triangulum Galaxy, let everything slow down. Let your thoughts drift like starlight across the void. We've traveled 3 million light years tonight, not with our bodies, but with our minds. We've seen spiral arms glowing with newborn stars. We've traced the invisible hand of dark matter. We've followed the light of ancient suns, light that left its source before humans ever looked up and wondered. Triangulum is out there right now, spinning in the dark, whether we observe it or not. Its stars are burning. Its gas is collapsing into new suns. Its story continues, written in gravity and light, in motion and time. And though we'll never walk on its worlds or breathe its air, we can still know it. We can still appreciate it. We can still feel connected to it in some quiet, unexplainable way. So let that connection linger as you drift towards sleep. Let the image of a spiral galaxy turning slowly through space be the last thought that crosses your mind. Let the vastness, the beauty, the ancient patience of the cosmos carry you into rest. You are small, yes, but you are also part of something immeasurably large. You are made of stars. You are the universe looking at itself. And in that quiet truth, there is peace. Somewhere beyond our sky, beyond the Milky Way, Triangulum glows. And somewhere within you, something glows too. a spark of curiosity, a flicker of wonder, a light that connects you to every distant star, every spiral galaxy, every corner of the cosmos. Hold that light gently as you close your eyes. Thank you for drifting through the stars with us tonight. If you enjoyed this journey, consider subscribing. There are always more galaxies to explore, more stories to tell, more quiet wonders waiting in the dark. Sleep well, and may your dreams be filled with spirals, with starlight, and with the soft, eternal turning of distant worlds. Good night.